Hi, Michael.
Hey, Charles, how's it going?
It is going quite fine. How's it going with you?
Well, this seems really exciting. It looks like maybe you're going to drive the next lesson.
I am going to drive the next lesson, and the next lesson is called Game Theory 3.
Game Theory 3.
Yes.
I feel like that presupposes the existence of game theories 1 and 2.
We have, in fact, done Game Theories 1 and 2. We did it in the last class, and so there's no point in doing it all over again.
Okay. But maybe people don't remember all of that?
Well, I'm sure they don't because I don't. So maybe what we should do is we should do another Scooby-Doo flashback.
And we can do this in a super special way.
Because
We're actually in the same place.
at the same time.
Yeah, it's crazy.
When's the last time that's happened? Yesterday.
Right, that's true.
But this is the first time we're actually recording something like this that we are able to actually do that in a way that it makes sense to other people.
Good.
So let's do the Scooby-Doo flashback. Would like to do it together?
Sure.
Let's do it together. Okay, you ready?
Uh-huh.
All right, let's give me. Okay, you ready? Let's
Ready.
Hi, Michael.
Hey, Charles, how you been?
I've been doing just fine. How have you been?
Good. It's been a while. I understand you went to Africa.
I went to Africa, the entire continent, or at least parts of it.
How's Africa?
It's fine. It's warm,
The entire continent?
the entire continent, or at least Kenya and Nigeria,
Okay.
particularly Nigeria, which was 80-something degrees and 4,000% humidity.
So do you want to do a shout out to any of your friends from there?
Yeah, I'd like to say hi to Chairman. I'd like to say hi to Prof. Oh, and Good Times. I'd like to say hi to
Nice.
Good Times. He was awesome. Okay, so Michael, I am back now so that we can talk about the last little section that we're going to do in this class. And it's game theory.
That sounds cool. What does that have to do with machine learning?
So that's an interesting question because, in fact, game theory comes from a tradition way outside of machine learning and AI. But you'll see in a moment why it is I care about game theory. And really, this is a very natural extension to all the stuff we've been talking about with reinforcement learning.
Interesting. And we're talking about games like Monopoly?
In some sense, we are, because all of life is like Monopoly. So, in fact, what is game theory? Maybe that's what we can do. We could just try to define game theory, and maybe it'll be clear why it is we're worried about this at all. Seem fair?
Yeah.
Okay. All right, Michael. So there's lots of definitions of game theory that we could use. One that I like in particular is that game theory is the mathematics of conflict.
That's interesting.
I think it's kind of interesting. Or more generally, it's the mathematics of conflicts of interest when trying to make optimal choices.
Because I feel like a lot of people have their own conflicts with mathematics.
I think everyone but mathematicians have their conflict with mathematics. I think that's fair.
I see.
But do you see can you see how worrying about the mathematics of conflict might be a sort of natural next thing to think about after you've learned a lot about reinforcement learning?
I guess the next bullet kind of suggests a trend. So we've been talking about decision making, and it's almost always in the context of a single agent that lives in a world and it's trying to maximize reward. But that's kind of a lonely way to think about things. So what if there's other agents in the world with you?
Right. And of course, evidence suggests that there are, in fact, other agents in the world with you. And what we've been doing with reinforcement learning, which has worked out very well for us, is we've been mostly pretending that those other agents are just a part of the environment. Somehow all the stuff that the other agents do is hidden inside of the transition model. But truthfully, it probably makes sense if you want to make optimal decisions to try to take into account explicitly the desires and the goals of all the other agents in the world with you. Does that seem fair?
Yeah.
Right. So that's what game theory helps us to do. And then at the very end, I think we'll be able to tie what we're going to learn directly back into the reinforcement learning that we've done and even into the Bellman equation.
Oh, okay. Nice.
Yeah, so that's going to work out pretty well. But we have to get there first, and there's a lot of stuff we have to do to get there. But right now, what I want you to think about is this notion that we're going to move from the reinforcement learning world of single agents to a game theory world of multiple agents and tie it all back together. As a sort of general note that I think that's worthwhile is that game theory sort of comes out of economics, and that in fact, if you think about multiple agents, there being millions and millions of multiple agents, in some sense, that's economics. Right? Economics is kind of the math and the science and the art of thinking about what happens when there are lots and lots and lots and lots of people with their own goals, possibly conflicting, trying to work together to accomplish something. Right? And so what game theory does is it gives us mathematical tools to think about that.
I feel like other fields would care about some of these things too, like sociology.
Right?
And what about? I could kind of imagine biology caring about these things too.
Even biology. I like the idea of biology. Biology. Why would biology care about this?
Well, I guess the way you described it in terms of lots of individual agents that are interacting, like, creatures that live and reproduce, I feel like they have some of those same issues.
Sure. So it's certainly biology at the level of entities, at the level of mammals or level of insects, you might be able to think about it that way. But perhaps even at the level of genes and at the level of cells, little viri and bacteria, you could possibly think about it that way.
Because they're in conflict too, I guess.
Yeah. Now, there's probably this notion of intention. It's not entirely clear what that means here. And I think implicit in the notion of what we're doing here is this notion of intention and explicit goals, as opposed to ones that are kind of built into your genes. But I think that's a perfectly reasonable way of thinking about it. I think the lesson from this discussion, though, is that what game theory sort of captures for us, or what we would like for it to capture for us, is ways of thinking about what happens when you're not the only thing with intention in the world, and how do you incorporate other goals from other people who might not have your best interest in heart or might have your best interest in heart. How do you make that work? And so if you think about that problem, then I think it makes sense that it's been increasingly a part of AI over the years, and in some ways machine learning has started to think of it as being a mainstream part of what we do.
Cool.
Hence why it's worth talking about today. Okay? Sound good?
Gotcha.
Okay, so let's try to make this concrete with a very simple sort of example. Okay, Michael, so here's a nice little concrete example to think about this. Let's pretend that we're no longer in a world of a single agent, like we've been thinking about with reinforcement learning, but we've gone full-blown generality to two agents, okay? And let's call those agents A and B. And they're going to be in a very simple game where A gets to make a choice, and then B gets to make a choice, and then A might be able to make a choice. So this tree that I've drawn over on the right is going to capture the dynamics of this specific game that I'm imagining. So these little nodes here, these circles represent states, and we can think about those in states in the same way that we've talked about reinforcement learning in the past. The edges between these nodes represent actions that one could take. So this should look familiar. This is just basically a game tree like anyone who's taken an AI course might have seen. Okay?
I guess so. It doesn't look like a very interesting game, but
No.
I guess it's a sort of abstract example.
Yes, it's a very simple game just so that we can get a handle on some basic concepts. So in particular, if you look at the details of this game, you start out in state 1, okay, and A gets to make a choice between two actions, going left or going right. If A goes right, she ends up in state 3. If she goes left, she ends up in state 2. Regardless, B gets to make a choice. From state 3, we can choose to go right, and really that's all that can happen. And what happens if B goes right from state 3 is that a value of +2 is assigned to A, okay? All of these numbers at the bottom, at the leaves here, are going to be values or rewards, if you want to think about them that way, that are assigned to player A. And in fact, for the purposes of this game, it's going to be the case that B always gets the opposite of what A gets. So if A gets +2, then B gets -2. If A gets +4, B gets -4. If A gets -1, B gets +1. Does that make sense?
Yeah, though, could you write it down so that I won't forget?
Okay, that's fine. So, by the way, this is a very specific kind of game here, and it has a name, which I want to get right. This is a two-player, zero-sum, finite deterministic game of perfect information. So, as a title or of a description of this kind of game, does this make sense to you? Do you think you know what they all mean? What all those words mean?
So 2 players because it's A and B. Zero sum because you said the leaves are A's reward and B's reward is the negation. So if you add the 2 rewards together, you're always going to get 0.
That's almost right.
Okay.
It's not exactly right. Actually, so zero sum really just means that the sum of the rewards is always a constant.
And that constant needs to be 0.
It doesn't need to be 0.
So if it added up to 11, that would still be 0 sum?
If it added up to 11 everywhere, yes.
Huh, okay. Interesting choice of terminology. Finite, I don't know. Everything seems to be finite here. There's no infinite number of choices or states or depth. Deterministic. Well, again, thinking about it in an MDP-ish kind of way, there's no stochastic transitions in this particular picture.
Right. So if I'm in state 2 and I go right, I always end up in state 4, period.
Right. Game, I guess a game is because it's more than one player.
Sure.
Of perfect information. That doesn't quite sound like the same terminology that we used in the MDP setting, but I'm wondering if that's like I know what state I'm in when I'm making a decision. So it's like an MDP as opposed to a POMDP.
That's exactly right. It's that you know what state you're in, and that's exactly what it means. It's like being an MDP versus a POMDP. That's a great analogy.
Cool. And does it matter that it's a tree like this? Because when we were looking at MDPs, we had more complex structures of graphs and things.
Well, you can think of this as unrolling the MDP if you want to.
Well, so then those states are sort of time stamped and history stamped.
For the purposes of this discussion, yes. And that's a perfectly reasonable way of thinking about it. Yeah.
Okay.
But in general, we're going to be thinking about game trees. But actually, we're going through all of this for nothing because we're going to discover pretty soon that none of this matters. But give me a couple of slides to get there, okay?
Sure.
Okay. So this is about the simplest, or at least the least complicated game that you can think about. A 2-player, zero-sum, finite deterministic game of perfect information. Basically, I can look at this tree, I know everything I need to know, and I can make decisions about what action I might want to take in order to maximize my reward. Okay?
Good.
All right. Now, in MDPs, of course, we had this notion of policies, right? You remember what a policy was, Michael?
Mapping from states to actions.
So in the game theory world, we have something very similar to policies. We call them strategies. So all a strategy is a mapping of all of all possible states to actions. So for example, here's a strategy that A might have. When in state 1, go left, and when in state 4, also go left.
That seems like a terrible strategy.
Does it?
Well, just if nothing else, just in state 4.
Sure. But it's a strategy, right?
Okay, but it's a strategy for one of the players.
Right, exactly. Each player has a strategy. And that makes sense, right? Before we talked about a policy of mapping from states to action, there was only ever one player, only ever one agent. And so we didn't have to worry about what other strategies there were. Here, when we talk about a strategy, it's always with respect to one of the players of the game. Okay, so question. I've just given you one strategy, which is what A does in all the states A could potentially end up in. How many other strategies are there for A?
For A. Okay, that sounds like a quiz.
That does sound like a quiz. Let's make it a quiz. Okay, Michael, so here's a quiz. Because you made me make it a quiz, I decided to make it even harder. So I want you to tell me how many different strategies are there for A and how many different strategies are there for B?
And you're talking about just deterministic mappings only, right?
Well, we are in a 2-player, zero-sum, finite deterministic game of perfect information.
So?
So yes, I mean deterministic.
Okay, all right. Because, it could be that it might be helpful to be stochastic.
Oh, that's true. That's true. So in fact, that's a good point. I was going to mention that later, but I'll mention it now. What I just wrote down here is actually not just a strategy. It's something called a pure strategy.
It's always about purity with you.
It is. Purity of chocolate and bacon mainly. But yes. So these are simple, pure strategies. Okay, so how many pure strategies are there for A and B?
Okay.
Okay, then let's go. Okay, Michael, you ready?
Yeah.
All right, what's the answer?
So I was thinking about A before you threw in the B. So let me not think about B yet. I'll just think about A. So you had said in state 1 it can go either left or right, and in state 4 it can go either left or right. So boy, that sounds a lot like 2 times 2 equals 4.
Yes, that's exactly right. So generally speaking, so actually walk me through that again, Michael. How did you get 2 times 2?
So, well, I had a little choice about how to think about it. One is that in some sense, if you go right from 1, then you don't really have to make another choice.
Right.
But if you go left, then you have this other choice to make of either going left or right. So if you're just writing it down as a mapping from state to action, you've got 2 choices at state 1 and 2 choices at state 4.
Mm-hmm.
And so that is 2 times 2, right? You can independently choose each of those.
Right, that's exactly right. So in fact, it's important there that even though if I had gone right on 1, I would never have to make another choice because I can't reach state 4. In order to be a strategy, you have to basically say what you would do in all states where you might end up.
Okay, that's fair.
Okay. All right, so what about B, using that incredible reasoning?
So, so B seems a little trickier because here it can only ever matter whether you're in, like if player A sends us down to the left, then we have a choice of 3. If player 1 sends us down the right, we have a choice of 1, which is really no choice at all.
Mm-hmm.
You can have any color car you want as long as it's black.
Yeah, like my Tesla.
I was thinking the Model T, but maybe T stands for Tesla.
T does stand for Tesla.
So, by the definition of how many different, sort of reachable strategies, it would be one answer. But if you're defining it the way you're defining it, it's going to be 3 times 1 or 3.
Yeah. And that's exactly right. Good, Michael. So let's actually write down what those strategies are. Okay, Michael. So I have written out, based upon your rather impressive way of thinking about it, all the possible strategies for A and all the possible strategies for B. A can go left, 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 right, right, left, right, right for states 1 and 4 respectively. And B can go left, right, middle right, or right, right.
Right.
Right. In particular, 3, in state 3, B can only go R, which makes B a
Conservative?
pirate.
Oh, that makes more sense.
It does make more sense. Okay, so now why did I write it this way, Michael? Well, I wrote it this way because if I write it this way with all the choices, all the strategies that B has up here and all the strategies that A have here, I actually form a matrix. And I can put in each of the cells of the matrix the value of taking a particular strategy from A and a particular strategy from B. Does that make sense?
Yeah, that's very clever.
Yes, it is very clever. I'm very happy that I came up with it entirely on my own. Okay, so let's start filling in these numbers. Or, instead of filling in the numbers ourselves, we could ask the students to do it by making it a quiz.
Nice. I
Shall,
see.
shall
Okay.
we do that?
Sure. Doesn't seem very hard.
Okay, so let's make certain that everyone here understands and what exactly we're asking you to do. We're saying that if, for example, A takes this first strategy, go left in state 1 and left in state 4, and B takes its first strategy, which is go left in state 2 and right in state 3, what is the value for A that will result? So let's actually do the first one as an example and ask everyone to do the rest of them. That seem fair?
Yeah, that's what I was going to suggest too.
Okay, good. So let's see. If A chooses to go left in state 1, since A goes first, we'll end up in state 2, right?
Mm-hmm.
And then in this first strategy, B goes left in state 2, which means we will end up going down this path, and the value there is plus 7. So 7 is, in fact, the value of this game with respect to A. Now, we know that because this is a two-player, zero-sum, finite, deterministic game of perfect information, that if A gets a value of 7, B gets a value of minus 7. So we could write minus 7 here, 7 comma minus 7 here, but since we know that it's equal and opposite, let's just write down the value for A, okay? Just for compactness sake. Does that seem fair to you?
Yeah.
Okay, cool. So with that in mind, let's see if we can fill out the rest of this table. Think you can do it?
I think so.
Okay. Then
Can you give me a place to write everything?
it will magically appear. Go. All right, Michael, tell me the answer. Let's go across.
All right, across. So the first row, it's all left, left, but the second left doesn't matter because that's in state 4. Oh, it might matter. I take it back. So left, left you did was 7. Left, and then player 2 goes to medium, middle.
Middle.
That would be 3. So then the payoff is 3.
Mm-hmm.
If the first player does left, left, and the second player does right, right, then we're going to go left, right, left again, or for a minus 1.
Mm-hmm.
Oh, wait, hang on. Left, right, left. Yes, yeah. The next row should be exactly the same as this one, except for in that third case. So it should be 7, 3, and the R, the difference there, the R and 4 only matters in this case where we've gone to the right state, right action from state 2, and so that should give us a plus 4. So 4.
Correct so far.
All right, halfway there. So, all right, now we've got something different. So now player 1 is going to the right. So now actually player 1's choice in state 4 never matters.
Mm-hmm.
So the next two rows are going to be identical to each other. And so in the first case, actually, all these numbers are going to be identical to each other. So player 1 goes right. Player A goes right. Player B has to go right. There's no choice. So we're going to get 2s no matter what now. So it's going to be 2, 2, 2. And then the second row will repeat that, 2, 2, 2.
Okay, so there you go. Michael, you are correct. You can feel very good about yourself. Very good, very good. So you're right, Michael. We do have this nice little matrix, and we have these numbers. And you know what's really interesting about this?
That we can figure out what the payoffs are for B without having to do any additional work.
That's true, but it's even more interesting than that, which is now that I've written down this matrix, nothing else matters. This whole tree, all these rules, none of it matters. It's irrelevant.
Okay.
Because everything about the game is captured here in this matrix. This is actually called the matrix form of the game, and it comprises everything you need to know about it. It doesn't matter what it means to go left or right, or what it means to go middle, or whatever. The point is, by following this strategy and this strategy, you end up with 7 for A. This strategy and this strategy, you end up with 2 for A, period. And how you got there does not matter.
But it does creep me out a little bit that what you're saying is that all that matters is the matrix.
You know, we should write a movie about that.
And I think it's been done, and it's scary.
Well, not the first one.
It was kind of scary. Like, people are trapped in this big box and their slurpiness.
But they're happy.
Yeah, but they don't know they're happy.
What do you mean they don't know they're happy? That's what it means to be. Oh, Michael.
Okay,
Michael.
speaking of which, now how do we figure out what do we do with this now? I mean,
So that's the big question, right? So what was the whole point of doing reinforcement learning? The whole point of doing reinforcement learning was to try to optimize your long-term expected reward, right?
Yeah.
And so you pick the policy that would get you to the best place possible. So here's a question I have for you. Given that this is everything we need to know, this little matrix of values, these are all the policies A could choose from. We're calling them strategies here, but strategies, policies. There are 4 A can choose from, and there are 3 B can choose from. What will you think A and B actually do?
Okay, so A wants the rewards to be high, so 7 is the highest. So A should choose the upper left corner.
But A can't choose the upper left corner.
Why?
A can only choose a strategy. B gets to choose its own strategy.
I see. So A is choosing the row, and then B gets to choose the column. So then
Yes.
B should choose that also, because that's what A wants.
No, B wants to maximize what B gets. And remember, B always gets the opposite of A because it's a 2-player, zero-sum, finite game of perfect information, deterministic or something.
So you're saying that if A chooses the first row, which
Say.
is the left strategy, then B now has a choice between 3 values and will choose the one that is worst for A, which would be
Yes.
the -1. So that would be a
Right.
terrible thing to do.
Yep.
Okay then. So then what if A chooses the second row?
Okay. If A chooses the second row.
So now, again, B is not going to let him have that 7, which is kind of sad. But still can't make it too bad for A. So like B would choose the middle right strategy, and then that would be a 3 for A, a -3 for B. But wait, hang on. So that was done thinking of it as A kind of making the choice first.
Mm-hmm.
That doesn't seem fair.
Okay, well then do it the other way.
All right. So if B chooses first, then B could choose the far right column because that's where the -1 is. That's where it's going to be happiest. See, B seems kind of mean. It's like it's happiest when others are suffering.
Well, but A's also happiest when others are suffering.
I see. So if B chooses that column, then A wants to choose the second row and get the 4.
Yep.
So B could choose the middle column,
Yes.
which then A would choose a 2.
A would choose.
and-
A would choose what?
One of the 2s, like one of the bottom 2 rows.
No, A wouldn't.
Oh, right. A's trying to maximize. So A would choose one of the top 2 rows. Oh, yeah, that makes more sense.
Right.
And choose a 3, which is better for B than having chosen the far right. And B could choose the far left column, but then A would choose one of the 7s, and B would be unhappy with that. So we'd end up with B choosing the middle column and A either choosing the top or the second row.
Mm-hmm.
So that's kind of the same answer we got the other way.
Yep.
Huh.
That's exactly right.
And was that just luck, or did you make this example to make that happen?
No, I didn't make this example to make that happen. In fact, the process you went through is exactly the process you would expect to go through, and you will always end up with the same answer. For a 2-player, zero-sum game, deterministic, finite, all those other words, the process you just went through is exactly the process you would expect to go through. So let's see if we can be a little bit more explicit about the process you went through. So in particular, the way I heard you write it down is that A must consider the sort of worst case counter strategy by B, right?
I see, because when A chooses the row, then B was going to make things bad for A along that row. So that's the counter strategy you mean.
Right. And in fact, when you try to do it the other way with B, well, B has to do the same thing. B has to consider the worst case counter as well. And in this particular case, the way we've set it up, where the value is for A is always therefore trying to maximize, and B is always trying to minimize A, which works out to be the same thing as maximizing itself. Does that make sense?
Yeah, I mean, other than the fact that, I named my first child Max, I really wanted to name my second child Min.
That actually would have been pretty cool. Why
Yeah.
didn't you do that?
Because I'm married to someone with more sense than I have.
Yeah, I understand. I completely understand. Okay, so A is trying to maximize, B is trying to minimize. They both have to consider the worst case that the other will do. And so what that's going to do is it's going to force them to go through exactly the process you went through, which is figure I'm going to make the choice so that if my opponent makes the counter choice, the worst case choice, I will end up as best as I can. So A is going to basically try to find the maximum minimum, and B is trying to find the minimum maximum. In fact, that strategy has a name, or that way of thinking about it has a name. What do you think it's called?
The minimum maximum.
Yes, or Minimax.
Which is a movie production company, I think.
No, that was Miramax. Do you recall that where you've seen Minimax before, Michael, in some other class that you once taught or once took years and years ago?
No.
Minimax was exactly the algorithm that we use for game search in Intro to AI.
Oh, which was a game tree, which is just what we started with in this case, even though we turned it into a matrix.
Exactly. So in the end, this matrix induces a game tree if you want to think about it that way, or game tree induces a matrix if you want to think about it that way. And the strategy then in sort of basic AI search and the strategy in game theory is Minimax. When you're in a two-player zero-sum game of perfect information.
So is there a way to do alpha-beta pruning on this?
All alpha beta pruning does is gives you a more efficient way of finding the answer.
I see, but it's the same answer no matter how you set it up.
Right.
Cool.
That's right. Okay, so this is pretty cool. So we have set up a kind of game where we have multiple agents, or at least two agents in this case, who have different strategies, and we actually sort of know, sort of in a world where it's a zero-sum game and the other person is trying to minimize what you get, maximize what they get, that the Minimax strategy would actually give you sort of an answer. In this case, by the way, we say that the value of this game for A is 3. If A does the rational thing and B does the rational thing, that is trying to maximize their own value, you will end up in this situation. That's kind of cool, don't you think?
Very cool. I feel like there should be a theorem.
There is, in fact, a theorem. I'm going to write it down. Okay, Michael, so here's this theorem that you so desperately wanted. You ready?
Yep.
I'm going to read it to you because you can't read. In a two-player, zero-sum, deterministic game of perfect information, Minimax equals Maximin.
All right, you told us what Minimax was, but you didn't tell us what Maximin was.
Well, Maximin is like Minimax, except the other way around. So A is trying to, one side is trying to minimize the maximum, and the other side is trying to maximize the minimum. It's
Okay.
exactly what we described before. It just depends upon whether you're looking at it from A's point of view or B's point of view.
Oh, I see.
Okay.
Like, do you choose a column first or do you choose a row first?
Exactly. So whether you go A first followed by B or B first followed by A, you're going to end up with the same result. And that more importantly, or at least as importantly, there always exists an optimal pure strategy for each player. In other words, you can solve those games and you know what the answer is. Once you write down the matrix, you just do Minimax or you do Maximin, and you end up with the proper answer. And now you know what the optimal players would do. Now, there's a subtlety here, which I got it a little bit in the previous slide when I talked about rational agents. And what we're sort of assuming in everything that we discuss here is that people are always trying to maximize their rewards. Okay? So we define the reinforcement learning problem that way. My goal is to find a policy that maximizes my long-term expected reward. So I'm trying to get the best reward that I can. And what you're assuming here is that everyone else is doing the same thing, and they're assuming that everyone else is doing the same thing.
Okay.
Does that make sense?
It does, though. I'm a little bit stuck on this word optimal at the moment.
Right. Well, that's what I'm trying to get at, actually, that optimal here really means I'm maximizing the reward that I can get, and I'm assuming everyone else is doing the same thing. And furthermore, I'm assuming that they're assuming that everyone else is doing the same thing.
So I guess I'm wondering whether this theorem is vacuous in the sense that are we defining optimal to be Minimax?
What we're defining optimal to be, I think, so that's a good question. I think I would unroll the vacuousness one level by saying this. Optimal here basically has to be optimal with respect to what? And the respect to what here is the underlying assumption that everyone is trying to maximize their rewards and that everyone knows this. So in a world where you have perfect information, it's zero sum, then the strategy of Minimax and Maximin give you the same answer. And that furthermore, there is always some place where the column and the row cross, the best column and the best row cross. And that is always going to be the solution to that particular game. Now, if we weren't in a two-player zero-sum deterministic game of perfect information, that might not be the case. But in a case where we're in this sort of simplest version, where everyone's being rational, that is optimal, that is trying to maximize their own reward, and is assuming everyone else is maximizing their own reward, this is the right thing to do. Now, I've got a little weasel word here as well, which we're going to get to in a moment, which is this notion not just of a strategy, but of a pure strategy. And there's a reason why we have notions of pure strategies, because in the end, as we get more complicated, we're going to have to deal with impure strategies. Okay? But are you with me so far?
I think so, yeah.
Yeah, that basically all that stuff we did in AI with game trees and search is kind of what you would expect people to do if they knew everything.
So I feel like I could prove this theorem in the case of trees because you just kind of compute values from the leaves up to the root.
Yeah.
And it doesn't matter. There is no notion of who goes first or who goes second. So there's just going to be one answer to that process. It's not obvious to me how to show it once you turn the tree into a matrix. That matrix, I guess, because it captures the same information, it ought to be the case that this is still true. But like I'd have to sit down and kind of think it through.
No, and so to help you think it through, I guess what I would suggest is if you have the matrix, you can create a tree that's consistent with it because every row and every column represents a strategy. You don't know what that strategy is, but you can, since it's a finite matrix, you can construct a tree that is consistent with that matrix. In fact, possibly an infinite number of them, I'm not sure, but you can certainly construct at least one that is consistent with it. And then once you have the tree, you just do what you say.
Good.
All right, good. So we've got this fundamental result. And now what we're going to do is we're going to try to be a bit more interesting. But it was important to go through this because now we've got some basic vocabulary and some basic building blocks. Okay?
Yep.
All right. So here's another game tree. We have, again, two players, A and B. And A gets to make a choice first to go left or right. And B will find herself in a situation perhaps where she gets to choose to go left or right as well. I've drawn these little square boxes, though, to represent chance. So what this means is that if A goes left, you end up in a chance box where you flip a coin, and 50% of the time you end up over here, and 50% of the time you end up over here. Along a similar vein, if A goes right and then B goes left, then you end up at another chance node, and 80% of the time you end up here, and 20% of the time you end up here. Alternatively, if B goes right, you always end up here. Does that make sense?
I think so.
So what we've done is we've gone from a two-player zero-sum deterministic game of perfect information to a two-player zero-sum non-deterministic game of perfect information. Okay? So we've relaxed. We've gone at least one level up in complexity. Okay, so do you understand this tree? Do you understand this setup?
Yeah, I think so. I mean, here the stochasticness is happening essentially at the leaves.
What does that mean?
That there's no choices to make for either player after this randomness happens. But that's not what you mean in general, right?
No, that's right. There could be, after here, you end up in a different state where you can then make more choices. But because I don't have enough room and because I want to make it simple, it just sort of ends after that.
Okay.
But yes, this tree could keep going on, and there could be random choices, chance nodes happening everywhere. There could have been a chance node that happened at the very beginning even.
I feel like I could work out the value of this game.
Oh, well, how would you go about working out the value of the game?
I would probably have it as a quiz.
Okay, but what would the quiz look like?
It would say, what's the value of this game?
Okay. Do you think that just having that be the quiz is the best way for someone to learn, or do you think maybe it can be done in stages?
Oh, I don't know. Do you have other questions that you want to ask?
Well, how would you go about determining the value of the game? I think the first thing you would do, at least if you were patterning after what we just did, is you would try to write down a matrix.
Sure.
So I'm going to write down a matrix so that our students will get a chance to work out what that matrix looks like, and then from there figure out the value of the game. Are you okay with that?
Sure.
Okay. So if we were going to do that, of course, the first thing we'd have to do is we'd have to figure out what the strategies are. So what are A's strategies?
I would have called them left and right, but they're not labeled.
Yeah, well, let's do that. Let's call them left and right. A can go left or A can go right. What about B's strategies?
B can go left or right.
And B can go left or right. Here's your first quiz question. In a world where A can go left or right and B can go left or right, what are the values that you would put in the cells of this matrix. Again, this is zero sum, so these values are from A's point of view, and implicitly there's we know what the values are for B, so we're just looking for the values from A. Okay, do you understand the quiz, Michael?
Yep.
Okay, so go. All right, Michael, you know the answer?
Yep.
Okay, what's the answer?
Do you want to know the value of the whole game?
No, I wanted to know the matrix.
Okay. So, right. So if A goes left, it doesn't matter what B does. And at that point, there's a chance node, and it's 50-50 for and -20, which I feel like ought to be -8.
Ah, that's right. How'd you get -8?
Because half of 2 is, or sorry, half of 4 is 2, and half of -20 is -10, so -8.
Right, so you just took the expectation of where you would end up. Beautiful.
Exactly.
Okay, what next?
And that it doesn't matter what B does. So the -8 is also in the upper right corner of the matrix.
Fair enough.
The next easy one to do is if both go right. If A goes right and B goes right, then we get the 3. It's just sitting there.
Mm-hmm.
And the last thing requires me to do some multiplication. So -5 times 0.8 is like -4.
Mm-hmm.
10 times 0.2 is like 2. So -2.
That is correct, Michael.
Shoo.
Yeah. So now we have the matrix. Now, what have we just noticed here? Remember what I said about matrices before?
It has all the information that you need.
Right. So, in fact, none of this matters. Who cares how we got here?
Wait, but
I love erasing stuff.
So here's the thing. We cannot reconstruct that tree from this matrix.
We can't reconstruct. Well, actually, we could reconstruct that tree from that matrix.
No, we can't.
Yeah, yes, of course we could.
No, we can't.
Yes, we can. Because there's an infinite number of trees we could do, and one of them is that one.
I see.
We just don't happen to know that it's the right one.
I don't think that's really what people mean when they say I can reconstruct this. Like I can reconstruct the crime at this crime scene. It could be any of a million things. Like no, we can't construct that specific tree.
But you know what? It doesn't matter because the only thing that matters is the matrix.
Ah.
And you will notice, Michael, that you did all that multiplication and you multiplied 0.8 times 5, and after a couple of seconds of thinking about it, which was probably edited out, but I know how long it took you to do it, you came up with the right answer. That's great. But notice that the number you came up with doesn't say anything about expected values and what the probabilities are. It doesn't even matter that it's non-deterministic. Because once you have these numbers, these expected values, that's what you're going to end up with. So who cares what the original tree was? Who cares if you can reconstruct it? Who cares what the rules of the games are? All you know is I have a choice of 2 strategies. We called them left and right here, but we could have called them 1 and 2 or Q and Z. It doesn't matter for the purpose of solving the game. So what is the solution for the game, by the way?
A is trying to maximize, right?
Yes.
So A would never, ever, ever, ever want to go left.
Mm-hmm.
So A is going to go right. And then B is trying to minimize, so B is going to go left, and we get the -2.
I believe that is correct. And it makes sense the other way as well, right? That B would not ever choose to go right because then A would choose to go right as well.
Gotcha.
So you'll still end up here. So here's, in fact, another theorem for you, Michael. So it turns out that theorem that we wrote down before is still true in the case of non-deterministic games
Oh, cool.
of perfect information, right? By the way, do you know whose theorem this is?
Charles's theorem?
No, although that would be cool.
Von Neumann's theorem?
Yes, this is von Neumann's theorem.
Oh, really?
Yeah. Did you just
Von
guess?
Neumann, man, he's responsible for everything.
Do you know, well, you're going to remind everyone who von Neumann is?
He's my uncle?
No.
No, you're right. You're right. Von Neumann, so we talk about von Neumann architectures in computer science. That the basic design of a microprocessor is still following the ideas that he worked out.
Right, the von Neumann machine. So there you go. So this is pretty good, right? So what have we learned so far? What we've learned so far is the only thing that matters is the matrix. And once you have the matrix, you use minimax, at least if you're in a 2-player zero-sum game of perfect information. At least if you're in a world of 2-player zero-sum games of perfect information, we can just write down this matrix, throw everything else away, and use minimax or maximin and figure out what the value of the game is, which is the same thing as saying as we know what the policy is, the kind of joint policy. In a world where everyone is being rational and trying to maximize their rewards and assumes everyone else is doing the same. That's pretty cool, I think.
Awesome. So, though, I feel like I could make a matrix that wouldn't have this property, this maxi-min equals mini-max, and that we couldn't make a tree out of it.
You probably could, but I'm going to guess that it's going to require that it's no longer zero-sum.
No, I'm going to say no to that.
Well, you know what? Now that I think I understand what you mean, and the answer is yes, you could. And in fact, that's what we're going to do next when we relax the next little bit.
Oh.
So would you like to do that?
Sure, though I'm afraid if we get too relaxed, we might just fall asleep.
In fact, why don't we do that? Why don't we take a nap and then come back?
The joy of being on video, asynchronous napping.
Done. Okay. I'll see you in a second. Okay, Michael, so here is another little game for us to play. And what I want you to notice about this game before I describe it to you in detail is that we have relaxed yet another one of the constraints. So we started out playing 2-player, zero-sum, deterministic games of perfect information. There was also a finite in there somewhere. From now on, we're just going to assume everything's finite because why not? And then what we did last time, just a few seconds ago, is we relaxed the deterministic part. So we had 2-player, zero-sum, non-deterministic games of perfect information. And now we are going to relax the requirement for perfect information. So now we're going to look at 2-player, zero-sum, possibly non-deterministic games of hidden information. And this is really important, Michael, because this last little bit of relaxation, going from perfect information to hidden information, is going to be a sort of quantum leap into the difficult problems of game theory. So this is where it starts to actually get interesting. So we've been building a foundation so far, and now we're going to get to the interesting and complicated stuff. Okay?
Wow. Yeah, I mean, one of the things that I learned just now is that the opposite of perfect is hidden.
Yes.
Like I always thought the opposite of perfect was imperfect. But okay, so hidden that's interesting. It's like I guess if I don't have a perfect face, I might as well hide my face.
Right, and that's in fact exactly the etymology of the phrase.
All right, I understand now.
Yeah, cool. It's in Wikipedia. Okay, so here we go. Let me describe the game to you. You ready? Mm-hmm. This is a version of mini poker where there's a set of cards, but they have no numbers on them. There are no faces. They're just red or black, okay?
Okay.
And red is bad for our hero, player A, and black is good for our hero, player A, okay?
I see.
So
Red. Why does it have to be red?
I don't know, man. You know, red. You know how it is. Okay, so here are the rules. They're all written down here on the screen, but let me walk through them with you. So A is dealt a card, magically. It will be red or black, and the probability of it being red or black is 50% each, okay?
Yes.
Right. So we have a uniform prior over the color. Now, remember, red is bad for A and black is good for A. So it's going to turn out, without loss of generality, that if A gets a black card, A is definitely going to hold on to the card, okay? Now, A gets this card, B, player B, does not get to see the card. A can choose to either resign or to hold. If A resigns, given a red card, then he loses 20 cents, okay?
Okay. Wait. So A is dealt red. A may resign but only if red.
Right.
And then A loses 20 cents.
Right.
Okay. All right.
Okay. So
Strange.
this is a betting game. It's not strange. It makes perfect sense. It's sort of a metaphor for life. Okay. Now A can choose to hold instead, hold the card, thus requiring B to do something. So if A holds the card, B can either resign or can demand to see the card. Now, if B resigns, then A gets 10 cents, regardless of the color of the card. Okay?
Yep.
Does that make sense?
Yep.
Okay. Now, if B chooses to see the card, in fact, demands to see the card, then if the card is red, then A loses 40 cents. But if the card is black, then A gets 30 cents. And since we're betting, this means that whatever A wins, B loses, and vice versa. That makes it zero sum.
Got it.
Okay, does this all make sense?
Yeah, I don't know if I can hold all those different numbers in my head, but the basic pattern of it is that, as you say, red is bad, black is good. If A gets a bad card, A can essentially either fold, right, resign, or kind of bluff, like, hey, I've got this great card, and then if B believes that the card is bad, then and calls A, and just folds, then A wins that. But if B says, no, I think maybe you're bluffing, and calls him, then everybody's rewards are more extreme, I guess.
Exactly. So it's just a version of poker. Weird version of poker, simple version of poker, but a version of poker nonetheless. There's a minor little detail here which isn't that important, but notice it's written that A may resign if it's red. Basically, A will never resign on a black card because it just doesn't make any sense. And so there's no point in writing it out. Okay? Because black is always good. Sort of nothing bad can happen to A if A gets a black card. So there's really sort of no point in writing anything out. But that's just a minor detail. Regardless, these are the rules. Okay?
Okay.
You got it?
Sure.
I'm going to redraw this as a game tree, which might make it a little bit easier for you to keep all of the rules in your head. Okay, so Michael, here's the tree version of what I just said. So remember, I draw squares as chance nodes, and so chance takes a chance, and half the time we end up in a state where where A has a red card, and half the time I end up in a state where we end up in a state where A has a black card. Okay, if A has the black card, then B gets to choose whether to hold or not. So in fact, let me add a little bit of color for you since you wanted some color. This is the place where A gets to make a decision, okay?
Yep.
And then this is the place where B gets to make a decision,
Got it.
okay? So A is going to be either in a red state or a black state. Only A knows this. B does not know this, does not know which state he is in. And so let's say A is in a black state. Well, A can only hold in that case, in part because it makes no sense to resign. And then B gets to decide whether to resign, and therefore A gets 10 cents, or to C, in which case A gets 30 cents. By contrast, when we're in the red state, A can either hold or resign. If A resigns, he loses 20 cents. If A holds, then B gets to decide whether to resign, and in which case A gets 10 cents, or to C the card, in which case A loses 40 cents, and B, of course, gains 40 cents. So this is just a tree version of what I just wrote. Does that make sense?
Okay. Yeah, I can see how this kind of captures the flow of information, but I feel like there might be a missing constraint to it.
So I don't know there's actually a constraint missing, but let me just point out something, and that is that B has no idea which of these two states he's in. Hence, hidden information. And because B doesn't know which state he's in, he doesn't know whether to resign or to C. In particular, if B knew that he was in this leftmost state, then he would always say C. If B knew he was in the rightmost state, then he would always resign. But he doesn't know which one, so it's not entirely clear what to do.
Neat. Where did you get this game? This game is awesome.
I got this game like I got all of the examples that we're using today from Andrew Moore.
He's clever.
He is clever, and I have shamelessly stolen all of his examples and materials for this. But he said it was okay by putting up slides in the world and saying, feel free to steal all of this stuff.
Do you want to write his name so that people can credit him?
Yeah, I'm going to write it at the very end when we talk
Okay.
about what we've learned.
Awesome.
Okay. So here's a question for you, Michael. We know that I wrote down a bunch of words which describe the game, and then I made it a tree because I could do that, and it makes it nice and easy to see what's going on. But now we know that, at least based on everything else we've done, we want to make a little matrix. And so we want to figure out what the value is for different strategies for A and B. So I'm going to assert, and I think it's pretty easy to see, I hope, that A basically has only two strategies. Either A is the type of person who resigns when a card is red, or A is the type of person who holds when a card is red.
Interesting. Okay. Yeah. Right. So it really is a conditional policy, right? So it's basically if red, hold or resign, if black, hold or resign. But your point is that black isn't really a choice, red is a choice, and there's only two choices. Okay, I can see that as the two strategies, sure.
Right. And of course, this does say does kind of say when you're in the black case, you know you're going to hold, so you know what's going to happen. Ultimately, B can either be the kind of person who resigns whenever A holds, or chooses to C whenever A holds. Right?
I see. So like in the previous trees, B would have four different strategies: resign or C in the left state, resign or C in the right state. Here there's this kind of extra connection, this sort of quantum entanglement between these two states that makes them have to be the same, so there really is just those two choices.
That's exactly right, although I probably wouldn't have used the phrase quantum entanglement. But yes, there's an entanglement, certainly. Since we can't tell which state we're in, you're either going to resign or you're going to C, and you just don't know what else to do. Okay, so A's a resigner or a holder, B's a resigner or a seer. So the question is, what numbers go in this matrix? And we're going to figure that out by having a quiz.
I kind of saw that coming.
Mm-hmm. Do you think you can figure this out?
Yeah, sure. Yeah, I think so.
Yeah, see? Yeah, I can do that. Okay, cool. So let's go then. Go. Okay, Michael, what's the answer? Let's start with resigner.
All right, resigner. Resigner. All right. E. So resigner versus resigner. So resigner, if A is a resigner, that means whenever A gets a red card, A resigns.
Yes.
And that would be a negative 20.
Yep.
But that's not going to be the answer, is it? It's because A doesn't always get a red card. A sometimes gets a black card. If A gets a black card, then a resigner, that means B is going to resign, and a plus 10 will happen.
Mm-hmm.
So those are the two possibilities, and they're equally likely. So it's a minus 10 divided by 2, which is minus 5.
Right. You are correct, sir.
Shoo. All right.
Which one do you want to do next?
Resign or seer.
Okay.
So again, good. This is a good choice because now it's the same argument as before, except for when we end up in that far right node, and that means minus 20 in half the cases, plus 30 in half the cases, which is a plus 10 divided by 2, or plus 5.
That's exactly right. Well done, Michael.
Thanks.
Okay, which one next?
So holder resigner. That means when A gets a card, A is going to hold the card,
Mm-hmm.
and that's true red or black.
Yep.
And then it's going to be B's turn, and B is going to... Oh, we're doing holder resigner, so it's going to resign.
Mm-hmm.
So, interestingly, I think that takes us to those two leaves, both of which are plus 10.
Yep.
Because why does that make sense? Because B doesn't get any... Right, because it's independent of the card. You actually said that when you explained the rules.
Mm-hmm.
So it's average of plus 10 and plus 10, which ought to be plus 10.
It is, in fact, plus 10. Well done. Okay, what about holder seer?
All right, so that's the case where A holds. So we go down those branches, and we always end up in one of the blue circled states.
Yep.
And B sees. Half the time that leads to minus 40, half the time that leads to plus 30. So that's minus 10 divided by 2, which is minus 5 again?
Yeah, that's exactly
All
right.
right.
So that's correct, Michael. And that's pretty cool, isn't it?
Yeah, I really like this game. I didn't think you could have anything that had sort of poker essence and be this tiny.
So we end up with this really nice little structure here. So I have a question for you. You ready for the question?
I'm trying to guess what it is, but sure.
Okay. Here's my question. What is the value of this game?
I was thinking that you might ask that. So can I step through it? Is that okay?
Yeah, sure. Go ahead.
So A is choosing the first row or the second row. So if A chooses the first row and then B chooses the column, then if it's the first row, B is going to choose the first column. So
Yep.
A is going to get minus 5.
Mm-hmm.
The same story is going to go through on the bottom row. If A chooses the bottom row, then B is going to choose the seer position, which gets the minus 5.
Right.
So from this, so it seems like the value of the game is minus 5. But now let's do the same thing on the B column. So if B resigns, now A gets to choose resigner or holder, and it gets a plus 10. And if B is a seer, then A chooses between resigner and holder and gets plus 5.
Yes.
So then from this perspective, it's the value of the game is plus 5. So here's a case where it better not be that we could take a perfect information game and put it into a matrix and get this out, because this is something that can't, like, it doesn't fit your theorem, right? We can't get the value of it by doing minimax or maximin.
Exactly. The problem here is that once you move to hidden information, minimax is not necessarily, and in this case definitely is not, equal to maximin. So von Neumann fails, as we all secretly
Idiot.
knew he would. Yeah, what has he ever done for us anyway? His theorems and his computer architecture that rules the world. Anyway, so we seem to have a problem here. And the problem is that once we go to this hidden information, as I promised, complexity enters in, Michael, and now we can't do something very simple with the matrix, find a pure strategy that's going to work. It really is the case that A strategy depends upon what B will do, and B strategy depends upon what A will do. And if you don't already know what that's going to be, you don't actually have a value for the game. And in some sense, you can get every single one of these values. So there's got to be somewhere around it.
I feel like that's sort of what you'd expect in a game like this, right? So because of the way that it is, if you know that I'm always a resigner, that I'm always going to what? That whenever I have a red card, I'm going to resign, then you know that if I don't resign, I have a black card, so you know that you should resign.
Mm-hmm.
Yeah, so it's one of these things where if I am really consistent and never bluff, say, then you can take advantage of me, and vice versa. Like if you always respond the same way to when I act a certain way, then I can manipulate that. So it's kind of like this game of this sort of mind game, right? Like I want you to not know that I know the thing that you don't know that I don't know.
Right, but the problem is that I know what you know, and I know that you know what I know, and that I know that you know that I know what you know that I know, what you know, what I know, what you know, what I know. And
Did
so
you really think
it
I
never
didn't know that?
And so you end up in this terrible situation. But there was a key word that you used there, Michael, and it was consistent. And everything that we've talked about so far, pure strategies, is exactly the same thing as talking about consistency. So the way we're going to get around this is we're going to stop being consistent, or at least consistent in the same way. Okay?
Yeah.
And the cheat here is that we're now going to introduce, instead of pure strategies,
Let's see. The opposite of pure,
is
impure,
mixed. That's exactly
Oh.
right.
contaminated.
No. So rather than sticking with pure strategies, we're going to start using mixed strategies. So what's the difference between a pure strategy and a mixed strategy, Michael? Well, it's simply this. A mixed strategy simply implies or means some distribution over strategies. So in the case of two strategies like we have here, where you can A can be either a resigner or a holder, we're going to simply say that the mixed strategy for A is some value for P, which is the probability of choosing to be a holder. So do you see what's going on here? So the only difference between a mixed strategy and a pure strategy is that for a mixed strategy, you choose some probability over all the different strategies that you might choose. So you decide that, going into this, I'm going to flip a coin, and half the time I'm going to be a resigner, and half the time I'm going to be a holder, say. Or 30% of the time I'll be a resigner, and 70% of the time I'll be a holder. Okay?
Yep.
Whereas with pure strategies, you always chose one or the other. So technically, it's the case that a pure strategy is also a mixed strategy where all the probability mass is on a single strategy.
Makes sense.
So in this case, we're going to, in fact, choose P to represent the probability for A of choosing to be a holder rather than a resigner. And so P can be 0%, probability 0, or it could be probability 1, or any value in between. You with me on that?
Yeah, that's neat.
Okay, good. To make certain you understand this, I'm going to give you a little quiz, which I have up here on the screen. You ready?
Oh, I see it. It's like those very square boxes. I
Yes.
didn't even realize what this could be about.
It certainly couldn't be a quiz because Charles has never drawn a straight box in his life. I hand drew those, Michael. It took me 17 hours.
Oh man, you're committed to this, and I appreciate that.
I am committed to this. Okay, so given that we have a mixed strategy and we have a probability P of A being a holder, here's my question for you. In a world where B is a resigner, okay, B is always going to choose to resign, what is A's expected profit? To make it easy for you, I copied the matrix over here in the upper right-hand corner.
Wait. If B is always a resigner,
B is always a resigner.
then what is A?
A is going to choose to be a holder with probability P.
Oh, so you want this to be a function of P.
Maybe.
If it's okay, sure, maybe. It could, well, I mean, yes, it's a function of P. It just might be a constant function that ignores P.
It could be in principle. Okay. Now, after you figure that out, I want you to decide in a world where B is a seer, B always chooses to see the card, what would A's expected profit be in a world where A will choose to be a holder with probability P? Okay? Got it?
And that's going to be, oh yeah, that could be different because it's a different strategy. Though, searing,
Yes.
like if you're a resigner, but if you're a seer, then what you're doing is searing.
Mm-hmm.
That would be an anagram of resigner.
How do you see these things?
I don't know. They're just there. The words just kind of mix themselves up. All right. Anyway, I think I'm ready to do the function. I'm ready to stop looking at the letters.
Okay? And go. What's the answer?
If B is the resigner,
Mm-hmm.
we don't really care about the other column anymore.
Mm-hmm.
Then what's going to happen is A is mixing between resigning and holding,
Yep.
and probability P is probably being a holder. So whenever that event happens, it gets 10, and whenever the opposite of it happens, it gets -5. So I want to say 10P plus 1 minus P5.
Okay.
minus-
Is that
Let me try that again.
Is that your final answer?
10P. Well, I could simplify it.
Okay. Well, then say it to me again. I'll write it out here so it's easy for you to see. Okay. And that is?
My answer.
That's fair. Do you want to simplify it? You don't have to.
Sure. Let me simplify it. So it's a minus P5 and a 10P, so that's 15P minus 1.
Minus what?
1,
Minus what?
5.
Mm-hmm. There you go.
Thank you.
That's correct. We would obviously accept either answer or any combination of those letters.
No, I think I might have to do this quiz over, actually.
No, not the one. I'm talking about either 15P minus 5 or 10P minus 1 minus P times 5 or 10P plus 1 minus P times minus 5 or any other combination that we can get Pushkar to actually bother to
Check.
Implement or check. Okay. Well, that was pretty good. And this, of course, is exactly the expected profit. As you put it, P times A is a holder and P times or P percentage, 1 minus P percentage. A chooses to be a resigner, and so it's just a weighted average between those two values.
So let me just double check that. So if P is 0, that means it never holds. It means it always resigns, and it gets -5, so that's right. And if P is 1, it means it always holds, so it should get a +10, and 15 minus 5 is 10. So boom.
Yeah, it works. You used math there. Very good. Okay, what about B?
B. So the same story except on the seer side.
Mm-hmm.
So yeah, I might need that space again. So 5. So oh, I see. Right. -5 times P
Mm-hmm.
plus 5 times 1 minus P.
Mm-hmm. If we simplify that, we get...
There's a -5 and another -5. So we get -10P
Mm-hmm.
plus 1
Plus what?
plus 5.
There you go. See, you learned. Okay, you want to check it?
Yeah, that's a good idea. So again, if P is 1, then that means you're always a holder, which should be the -5. And if we put in a 1 there, we get 5 minus 10 is -5. And if P is 0, that means we're always a resigner, and we should get a 5 for that. And yeah, so we zero out the -10, and we get the 5.
Exactly.
Now, it's not clear to me why we're playing this game. Oh, it is clear to me why we're playing this game. Because we want to figure out something about a strategy that is mixed.
Right.
So this is how well a mixed strategy does, but not against another mixed strategy. This is against 2 deterministic strategies.
Ah, but is it, Michael? But is it? So,
Okay.
I'm going to notice something here, which is that you, as you astutely pointed out earlier, we have 2 functions of P, or 2 equations of P. And by the way, do you know what they are? They're lines.
Sure, because it's linear in P, so that's what linear means.
Right. So what would happen, do you think, if we were to actually draw these lines?
I think we'd have 2 lines.
Yes, and what would those 2 lines look like? Let's take a look, shall we?
Sure.
Okay, so what I've done here, Michael, is I have drawn both of these lines. So here's the line, 15P minus 5. This is the case when B is a resigner. This is my best attempt at drawing it to scale. You start out -5, as you point out, and you end up with +10. And this is the line where B is a seer. That's -10P plus 5. So you start out with +5, and you end at -5. Okay?
Cool.
So what do you notice about these 2 lines?
They make an X, so they intersect.
They do intersect. Can you tell where they intersect?
How would I solve that?
You'd have a quiz. Okay, Michael, so here's a quiz. Where do the 2 lines intersect? Think you know how to figure it out?
Yep.
Okay, then go. Okay, Michael, what's the answer?
I don't know, but here's how I'd get it. I'd set the equations of the 2 lines equal and find the P where those values are equal.
Okay, so here, let's do that.
And I feel like that's like 25P on one side and 10 on the other.
Okay.
So like 10 over 25, which is like 2 over 5, which is like 2 over 5.
Yes, which is also 0.4. So 0.4, that's exactly right. And you should do it exactly the way you said. Set the 2 equations equal to another, do simple algebra, and...
So what would have happened if P ended up being like not a probability?
then they wouldn't have crossed inside.
Good point.
So, by the way, here's a question for you. We can make it a quiz, but I'm not going to make it a quiz. What is the value of the game at P equals 0.4?
So I just plug it into those equations. And so -10 times 0.4 is like -4 plus 5 is 1. So I'm going to say 1.
Mm-hmm. So the value here is, in fact, 1 cent. And if you put it in the other equation, you get the same thing.
Yes, right, because they're equal there.
That's actually the answer to the entire kit and caboodle.
Sorry, where were the kittens?
If A chooses a mixed strategy where with probability 0.4, he chooses to be a holder, notice that it doesn't matter whether B is a resigner or B is a seer. You will end up here, and there will be a value of plus 1 penny to A.
On average.
The expected value is plus 1.
Neat.
Now, you might ask yourself, well, what if B decides to be a smarty pants and also do a mixed strategy? What do you think would happen in that case?
So, of course, it changes something, but it doesn't change the value of the game because if B is a resigner, A is getting 1 on average. If B is a seer, then A is getting 1 on average. And any convex combination of 1 and 1 is going to give us 1.
That's exactly right. So, in fact, if you think about it, if B tries to do a mixed strategy between these 2 lines, it's going to have to be for every single point between the 2 lines, somewhere, the average is going to have to be somewhere in between there, no matter how you weight that average.
So it's like a bow tie is the space of possible payoffs.
Right. And since for any, let's say if B decided to pick some, some value such that it's in this region of the space and it's going to end up somewhere, say, between here, that's fine, or here, that's fine, or here, that's fine, or here, that's fine, or here, that's fine. More importantly, right here, it's going to have to be between the two lines, but those two lines cross. So no matter what mixed strategy B chooses, on average, we will end up here. So the value of this game is the expected value of this game, and it is +1 for A.
Now hang on. So why is that? Why is it not? I mean, there's other values that could be obtained. There's a -5, there's a +5.
True.
Like, why is it +1?
Well, it's +1 here on average. On average, the expected value of this game is +1.
So you say that the strategy for A is to choose 0.4, but why? Like, why is that, of all the different values, it's just because the lines intersect? I don't understand what makes that a good idea for A. Like, it's not like it gets any additional payoff for having things intersect.
Well, if A is going to choose a mixed strategy and B is going to choose a mixed strategy, this is the mixed strategy for A that guarantees an expected value of +1. Meanwhile, so imagine that this is the way you're going to set it up. So we've been kind of talking in general that A is going to choose a strategy, B is going to choose a strategy, then they're going to go. And that because we know everyone's rational, you already know which strategy B is going to pick, and B already knows which strategy A is going to pick, right? Because we made this assumption about everyone's trying to maximize their own utility or their own reward. So in a mixed strategy, if you know you're going to go for a mixed strategy, you have exactly the same situation. B can figure out, well, what is it that A should choose? And A can figure out what is it B should choose. So notice that in this particular version of the game, the way it's set up, even if A announced beforehand to B, listen, I am going to choose to be a holder with probability 0.4. It doesn't matter what B chooses. The expected value is this. It's +1, right?
Yeah.
But imagine that A said, well, I'm going to choose to be a holder with probability 1. Well, then what should B do? B should choose to be a seer.
Right.
It's exactly the situation we were in before.
Okay, but here's the thing I'm having trouble wrapping my head around. So it's not special that it's an intersection. What's special maybe is it that, if B is always okay. So taking what you said before, that A is going to announce a strategy. So for anything that A can announce, B is going to presumably do whatever's best for B.
Right.
Which is to minimize, right?
Mm-hmm.
So if you look at that triangle at the bottom, if you think about that as those lines, that V, upside down V shape, yeah, exactly, that thing. If you think about that as being the payoff function for A as a function of the probability P that it chooses to hold, then we've chosen the maximum.
Right.
Right? We're trying to find the probability for which A gets the highest expected value, and that it's at that peak there.
But notice something, Michael. For any case where the two lines cross, you're going to have a function of this form.
Well, let's be sure of that, because I was thinking that was not true. Because basically, in this case, we have a line of positive slope and a line of negative slope. Right? So what if we can have an intersection between two lines of negative slope?
So again, by doing the same exercise you were doing before, where you you sort of take the minimum of the two lines at all points.
Yeah.
You'll end up with this. Where do you pick it then?
The far left, P = 0.
Yeah.
But not the intersection in particular.
No, that's true.
Okay, all right. I wasn't quite getting that. But so the intersection is special because in some cases that is where the max is. I guess the max can only be in those three places, right? It could be far left, far right, or the intersection. There's no other way to have a maximum of lines.
Right. And by the way, there's another case like this where they never actually cross. Or like this where they never actually cross.
Got it.
Right. But in either case, right, it's always going to be those 3 points. It's going to be the extreme or where they cross. If they happen to never cross, then that point goes away. And so you just pick the maximum. So in fact, if you wanted to think of an algorithm to choose the right thing to do for A, you basically plot the lines. You take the min at every point, and you find the maximum point.
Oh, I see. So you could just kind of discretize it almost.
Yeah, and you're done. Seem reasonable?
Well, discretizing seems problematic, but I get that we're trying to find the probability so that we maximize.
Right.
Oh, wait, we maximize the minimum of the two other things. So it's like maxi-min again.
Yeah. Except here, so in fact, it is exactly minimax or maxi-min, except, well, I guess if you're thinking it from A's point of view, it's minimax or maxi-min, but in this case, there's this other parameter, which is the probability, which is how you determine how you're doing the minimax.
Got it. Right. In this bigger space, it's mini. I see. Yeah. That makes sense. What about but why is A the one who needs to be random? Why isn't B the one who needs to be random?
It's you end up with the same. You end up in the same place. Because again, remember, you're doing this kind of optimal notion where underneath all of that is this belief that both people are going to be rational. So the only reason to do this, to take the maximum minimum, is if you believe that B is always going to try to minimize what you do. But B's in exactly the same situation, right? From B's point of view, that's what's happening.
Huh. It's the same equations?
Yeah, it gets turned around. That's actually an interesting exercise. Maybe that's a nice homework assignment.
Okay.
So does that all make sense to you? Now that we've
looks a
said
little
it
green
15
and
times.
scribbly, but yeah, sure. That's cool.
That's how you know when you're done, Michael, when it's all green and scribbly.
Does this generalize to more than 2 options? It seems like it's going to get messy fast.
Yes, it does. It generalizes to more than 2 options. Effectively, now you're just doing a max over n things instead of 2 things.
And you have to search for, there's possibly way more intersections to worry about.
Yeah, but all you care about is the minimum. Think of it as you're always drawing the minimum function. Okay, Michael. So, feels like we've relaxed almost everything we can relax except for one thing. We're now going to look at 2-player non-zero sum, possibly non-deterministic games of hidden information.
Cool.
And that's going to turn out to be messy, but get us to the place where I've secretly been trying to get us all along. So let me describe a game for you very carefully, and let's see where it leads us. Okay, here's the game. You've got 2 people. These 2 people are criminals.
Oh, no. Are they smooth criminals?
One of them is. You're terrible. Okay, so we have 2 people. They're criminals, okay? And unfortunately, they've both been captured by the cops. I have actually no idea how to draw that, but let's just try to draw it like this. The cops come along and capture them both because they are suspected in a particular robbery, okay? And they take them and put them both in jail. So those are jail bars, okay? But they don't just put them in jails, they put them in 2 separate jails.
Oh, no.
Okay? And one cop goes to one criminal and says, listen, here's the deal. We know you did it, okay? We know you did it. And your friend over there, he's currently singing like a bird. And he is going to pin it all on you. So this is your last chance to give us a little help and admit that you 2 did it, or that the other guy did it. If you admit that the other guy does it, you said it was his fault, then we'll cut you a deal. Now, to make it worse, the cop tells him that there's another cop over there who's talking to the smooth criminal and is offering him the same deal.
Yeah.
And whoever goes first, whoever pins it on the other guy first, gets to walk. Okay? So, if I can get the curly head guy to defect, okay, then I am going to let him walk, and he will spend 0 months in jail.
Okay.
Okay? On the other hand, if the other guy defects, then he's going to get to spend 0 time in jail. And since we've got all that we need, we got a confession to get this guy to go to jail, he's going to go to jail for 9 months. Okay?
Negative 9 months?
Yeah.
That's a cost in months.
Yeah, that's
a
a cost in months. Okay? So if curly-haired guy defects before the other guy does, then 0. He walks. He pays no cost, other than the cost he's already paid for a life of crime. Now, if he refuses to drop a dime on the other guy, but the smooth criminal decides to defect, he's going to lose 9 months. Does that make sense? And the other guy's going to walk. So he's getting the same deal. They're both getting the same deal. You got it?
Yeah.
All right. Now, it's a little more complicated than that. All right? I hope you're keeping all this in your head. It's a little more complicated than that. There's actually 4 choices here, not just 2. It's not just a case of I defect or the other guy defects. I defect, the other guy doesn't. I don't defect, the other guy does. Okay? You could both refuse to drop a dime on the other. You could cooperate. Or you could both rat out the other.
At the same exact moment?
At the same exact moment. So
Okay.
There's a big, thick wall here. Curly guy doesn't know what smooth guy is doing, and smooth guy doesn't know what curly guy is doing.
Right.
So the question is, if you have a choice between either defecting or,
Which means blaming the other
which
guy.
means blaming the other guy, you're defecting from your friendship.
Oh.
Or you can cooperate, that is, be true to your friendship. Both people can defect, both people can cooperate, one person can defect, and the other person cooperates. So there's actually 4 different options there.
I feel a matrix coming on.
Yeah, I think there's a matrix coming on. So let's draw the matrix because I think that makes it easier to see. But you have the background here, right?
I think so, yeah.
The key piece here is that each person has a choice of either defecting from their friendship or trying to cooperate, keeping their mouths shut, and they don't know what the other person is doing. So what are all the costs here? What are the worst case things? So let's just draw it all out as a matrix. So let's just call the smooth guy A because that's what we've been doing all along. And he can either choose to cooperate or he can choose to defect. Now, by the way, I'm saying cooperate and defect here because they're terms of art, not because these are the words I would have chosen. Okay? B can do the same thing. B can choose to cooperate or B can choose to defect. Now, I've set up the game in a particular way here. The cops have set up the game in a particular way here. If B defects but A cooperates, then B gets to walk and A has to pay the price, 9 months in jail. So I'm going to put into this cell -9, 0. So this means this is the value of this set of strategies for A, and this is the value for B. So the first number in the pair is what A gets, and the second number is what B gets. Okay?
Got it.
You with me? Okay.
Yep.
Now notice we have to do this now because it's no longer zero sum. It's not going to always add up to a constant.
Oh, well, it is. So far, it's a constant. It's -9.
That's right. Oh, and in fact, it looks this way as well because I have a symmetric deal here. So if A defects and B cooperates, A gets to walk and B goes to jail for 9 months. Okay?
Yep.
So right now, you're right. It's looking like a zero-sum game, but it isn't. Because what happens if both A and B drop a dime on each other? Well, they both confessed. So it's a little good. It's a little bit better than having one of them, only one of them confess. The deal that the DA is willing to give them is that both of them will spend 6 months in jail. Now, these are just the numbers that are a part of the game. I'm not computing this from anywhere. This is just the way the cops have set this up. And now what's an interesting question here is what happens if both A and B keep their mouth shut? They both choose to cooperate. It turns out that it's not a perfect world because they were caught with a bunch of guns they didn't have permits for. So if neither one of them admits to robbing the bank, they're still going to do a little bit of time. But in this case, it's a small weapons charge, and so each only spends a month in jail.
I see. So now it's definitely not zero sum because we have a -2 there, -12 there, a -9, and a -9.
Right.
Okay.
Okay, so you got the game? You understand it?
Yeah, I think so.
It's very simple. Now, just looking at this, what's the best possible outcome for the two of them?
So if they cooperate with each other, then there's 1 month later, they're back on the streets, back to their criminal activities.
Or they're reformed. You never know.
Sure. Back to their choice of whether to have criminal activities. The mutual defection one, where they both defect, it's either 12 months or 6 months, depending on how you think about it, but they don't do nearly as well. And then the defect and cooperate, it seems like there's a lot of incarceration that will happen. So it feels like the best for the two of them is the mutual cooperate.
Yeah, and that makes sense. This is sort of what you want to happen. Both of them keep their mouths shut. They do a little bit of time, but on average, they do pretty well, right?
Yep.
So my question to you is that going to happen?
Sure. Why wouldn't it happen?
Well, you tell me. If I know that you're going to cooperate, let's say that I'm A, okay, and you're B, and I know that you're going to cooperate. What should I do?
You should cooperate.
Should I? You've chosen this column, right?
I see. Well, if you think of it that way, that it's not a joint choice, but it's actually an individual choosing, then you're better off defecting because then you get off scot-free.
Yep.
But I go to jail for 9 months. I could have a whole baby in that time.
It usually takes closer to 10, but sure. But you go to jail for 9 months. I don't.
So if you are just that cold, I guess because you're a criminal.
It doesn't matter. Remember, the matrix is everything. The value of doing this to me is 0 versus -1.
All right. That's cold, man.
I agree, but it's what the numbers tell you. What if it wasn't criminal? What if it was just, the amount of money that I was going to win in a mini poker game?
Yeah, but it's a different kind of mini poker game because it's like you beat me, But by beating me that way, you like nearly killed me.
So, are you saying
What
that
do you mean,
when?
so?
Are you saying you always let me win whenever we play poker?
No.
Okay, then. Because you're cold. Is that what you're saying?
No.
Exactly.
Wait, what?
Right. So the point, Michael, is that if I know you're going to cooperate, you're going to choose this column, then I should defect.
Okay. All right. So fine. So now I'm going to jail for 9 months.
If you choose to cooperate.
Aha. If is good. So what you're saying is, I could drop a dime on you.
You could. So you could choose to defect, and if I knew you were going to choose to defect, what would I do?
Well, you already showed your colors, man. You're defecting. So I'm just switching. I'm just saving myself 3 months by ratting you out.
Yeah. So we would end up here. By the way, you know that this game is symmetric, right?
No, you defected first.
No, here's the thing. Since the only thing I care about is maximizing my own reward, my own value, I'm going to do the thing that makes sense for me to do in this case, which is if you cooperate, defect. If you defect, defect. But you would do the same thing because your whole goal here is to maximize your value.
Yeah, well, you don't know me like that.
Yes, I do, because it's everything that's here in the matrix. This is the wonderful thing about game theory. All the stuff that you're concerned about, it's all inside the matrix. Remember, the rules of the game don't matter. There's no prisoners here. There are no criminals. There's just I get $1, I lose $1, or I lose $0. I lose $9 or I lose $6. Or, for that matter, cents. I lose 1 penny or I lose no pennies. I lose 9 pennies or I lose 6 pennies. It doesn't matter. This is the value of these particular strategies, and I'm going to want to defect if you cooperate. You'll notice if you defect, I'm also going to want to defect. In fact, if you look closely at this matrix, you should notice something, Michael. From A's point of view, when does it make sense for me to cooperate versus defect?
You mean if you have some kind of probabilistic policy over cooperate and defect?
No, not even that. Just in general, is there ever a time as A that I would rather cooperate than defect or vice versa?
Oh, I see. So if I know you're going to cooperate, I should defect to save myself a month. But if I know you're going to defect, I should defect to save myself 3 months. Either way, I'm coming out ahead.
Right. So in fact, let's take a look at this. If I look at the value for me as A between cooperating and defecting in this first column, it's -1 versus 0, right? Which number is bigger?
0.
Right. If I look at it in this column, it's -9 or -6. Which number is bigger?
-6.
Right. In both cases, defecting is better than cooperating. So in fact, this choice, this strategy dominates the other. In other words, it is always better for me to defect than cooperate. So I will never cooperate, ever, because it's always better for me to defect.
So fine. So I'll never cooperate ever. That'll show you.
By exactly the same argument, -1 versus 0, -9 versus -6, defecting is always better. B will never cooperate. What's the only thing that's left?
Pain.
Pain. This is called the prisoner's dilemma.
Huh. You said it was simple, but it seems kind of evil.
I didn't say it wasn't evil. Those things aren't opposite of one another. It's not like perfect versus hidden or pure versus mixed. It's not easy versus evil. Evil's often actually easier.
It's easy and evil.
So we're in a little depressing place here, Michael. You claimed in the beginning, and I agreed with you, that this is sort of the best option. You want everyone to cooperate because that's sort of what's best for the group. But because defecting dominates cooperating both for A and B, you're going to end up here, at least if you reason about it that way.
Yeah, I see that.
Hence, prisoner's dilemma. The only way to break this is if somehow we could communicate and collude with one another so that we could guarantee that we would both choose to cooperate at the same time.
So that's that wall. What if you put a Skype connection between it or a Google Hangout?
Well, if you were forced to say what you're going to say at the same time, or somehow be able to punish someone maybe for, not doing the right thing, then you might be able to make a different decision. But for this very simple version where I'm going to do it once, even if I could hear what you had to say, if whichever one of us went first, the second one would always be able to take advantage of that.
I do find this kind of depressing.
Yes, it's a dilemma. It's a true dilemma. So this brings us to a more general sort of strategy. This whole notion of strict dominance works in this case, but you can imagine very complicated large matrices where it may not work. But it turns out there's a generalization of this notion of dominance that works remarkably well, and that's what people tend to use to try to solve these kinds of games to find out what the true value of a game is. So let me describe that for you, okay?
Okay.
All right, Michael. I'm going to define a new concept for you. It is called the Nash equilibrium.
Nice.
Okay. Here's the setup. You have n players. So we've moved beyond simply 2 players. You have n players. And each player has strategies it can choose from. So here I'm referring to them as S1. These are all the strategies for player 1. S2 are all the strategies for player 2. Up to Sn, all the players for strategy n. Got it?
Yep.
Okay, so each of these are a set. So I'm going to say that the particular strategies, S1 star, S2 star, S3 star, so on and so forth, Sn star, that is a strategy that each of the n players has chosen, is in a Nash equilibrium if and only if, for each one of those strategies chosen by the n players, it is the strategy that maximizes the utility for that particular player. It is the strategy that maximizes the utility for that particular player given all the other strategies that were chosen. Now, I actually find that very difficult to kind of work through, so let me try to say it a different way. Given that you have a set of strategies, S1 star, S2 star, S3 star, Sn star, we know that they are in Nash equilibrium if, and only if you randomly chose one of the players and gave them the chance to switch their strategy, they would have no reason to do it.
Interesting. Okay.
So does that make sense?
Yeah.
Right. So an equilibrium, right, just in general, the word sort of makes sense. Right? An equilibrium is at a place where everything is balanced. Right? And in some sense, there's no reason for anything to move because they're in balance. So we say that a set of strategies are a Nash equilibrium if no one person has any reason to change their strategy in a world where everyone else's strategy remains the same. Then you're in equilibrium, and in particular, you're in a Nash equilibrium.
Nash equilibrium. Okay, good.
Do you know who Nash is?
Ogden Nash was a poet.
Not that Nash.
I think there was a TV series with a Nash in it.
Yes, there was.
But you're thinking of John Nash,
That's right.
the Nobel Prize winning person who's featured in the movie A Beautiful Mind.
Yep. That's exactly right. And it was, in fact, a beautiful equilibrium. Okay, so there's the notion of a Nash equilibrium. It was invented by John Nash, if you believe the movie, in order to pick up women. Which I've never seen this movie.
Oh, really? Oh, I watched it, and it was surprising how unhelpful it was in explaining what a Nash equilibrium was.
I'm not surprised. I hope this is helpful, though. So it really is a kind of difficult concept to completely wrap your mind around. But what it really boils down to is, listen, if we all picked a bunch of strategies, and we knew that one other person, one of us, we don't know who beforehand, but we know that one of us would have the opportunity to change their strategy after they see what everyone else's strategy is. We'd be in a Nash equilibrium only if that person, whoever that person is, has no reason to change their strategy.
Gotcha. So specifically, you made a distinction between strategies that were pure and strategies that were mixed.
Right.
And I guess I don't see in this case which kind we're talking about.
Right. So in this particular case, we're talking about pure strategies. However, exactly this wording works with mixed strategies.
Oh, I see. So you can have a pure Nash equilibrium or a mixed Nash equilibrium.
Right. And so you could, each one of these, instead of choosing a particular strategy and saying they're Nash equilibrium, you could talk about a probability distribution over each of these sets of strategies and say those are in Nash equilibrium if no one would want to change their probability distribution.
Got it.
So this works for both pure and mixed. All right, so you think you understand this?
Sure.
Good. We will test that. Okay, Michael, so you think you know everything, so here's a quiz. So here are 2 matrices, matrix prisoner's dilemma and matrix a bunch of numbers that look vaguely symmetric but aren't quite. So here's what I'm going to ask you to do. In each of these cases, find the Nash equilibrium.
Uh-oh. So you told me what it was, but you didn't tell me how to find them, so that seems kind of rude.
It was implicit. It's intuitively obvious, even to the most casual observer.
Oh, well then, okay. So, and just to remind me now, each row and column is a choice for one of the players or the other player.
Yeah.
And the first number in the pair is the row player, or A's payoff, and the second number is B's payoff.
Yes.
And we might need probability distributions, or we might not, depending on what it takes to be in Nash equilibrium.
Right.
Okay. I don't. I'm not. It's not like I see the answer yet, but I either will be able to find it or I won't. At least I understand the question.
Okay. And by the way, just to make it easier for you, there are pure Nash equilibria here. Okay? All right. So you ready?
Yep.
Just circle the one or underline it or whatever it is Pushkar does to make it so that you can answer this quiz. You ready?
Totally.
Go. All right, Michael, you got the answer?
I'm ready to try to figure it out.
All right, let's go. Let's try the first one.
I feel like the first one's going to go rather well. So we need a pair of strategies so that no player is motivated to switch.
Mm-hmm.
And you told us they were pure strategies. So we actually have a nice algorithm for doing this, which is we can just check each one of them with the definition.
Mm-hmm.
But in the case of Prisoner's Dilemma, I think a natural place to start would be that -6, -6.
Mm-hmm.
So let's say that A chooses the second row and B chooses the second column. Let's see if that's a Nash equilibrium. So both players need to be happy. So would A be happier switching? If A switched, it would be getting -9, which is worse. So A is happy where A is. And if B switches, B would be getting -9. So boom, Nash equilibrium.
Done.
Now, I didn't verify that other ones weren't a Nash equilibrium, but you didn't say find all of the Nash equilibrium. You just said find, well, you did say find the. So you kind of implied that there's just one.
Right, but actually that's true. But you don't have to check this because we already went through an exercise where we knew the answer was -6, -6. And the way we did that is we noticed that for A, defecting, the second row, is always better than this, right? And that in particular, this row strictly dominates this row.
Right.
Which implies that if I picked anything on this row, I would rather move to the other row. And you can see it. -1, up, 0 is better. -9, up, -6 is better. That's what it means to be strictly dominated. So I'd never pick this row anyway. And the same argument for B for this column. So you'll notice that by getting rid of the things that are strictly dominated, the only thing we're left with is this. And it turns out, in fact, to be a Nash equilibrium. So this is correct.
So you just told me how to do my job, which makes me a little sad.
Well, in this
because I already
case-
had the answer to this, but maybe you were signaling to me how I might attack this next problem. Maybe. So A is choosing a row and gets the first number. So, is there a row that dominates all the other rows? It doesn't seem that way.
Mm-hmm.
But maybe okay, let's start with B. Maybe there's a column that dominates all the other columns. But no, it looks like it's totally symmetrical.
Yep. So strictly dominated doesn't necessarily help here. And by necessarily, I mean doesn't.
So that was kind of mean.
Thank you.
All right. So, but we have something else we could do.
Yes.
So there is the largest number that anybody can get is 6.
Mm-hmm.
And there's a play where both of them can get the 6.
Yep.
So there's no way they're going to want to switch away from that because everyone's getting their kind of maximum amount of reward. So A, bottom row, B, right column gets us a Nash equilibrium.
And that is, in fact, correct. And you can see it because from here, it would always be worse for me, and it would always be worse for me. So these are, in fact, the Nash equilibria for these two problems.
Cool. They've seemed easier than I was expecting.
Mm-hmm. So here are 3 fundamental theorems that come out of all of this work on Nash equilibria. They're all on the screen in front of you. I'll read them for you just in case you can't read my handwriting or if there's some typo that you discover that forces me to erase some words and then write some new ones. Okay, are you ready? All right, the first one is, in the in-player pure strategy game, if elimination of all the strictly dominated strategies eliminates all but one combination of strategies, then that combination is, in fact, the unique Nash equilibrium. So that's what happened in Prisoner's Dilemma. We got rid of all but one option, and that option had to be the unique Nash equilibrium.
You say eliminate all of them. Is it possible that things that we couldn't eliminate in one round, we could eliminate in the next round?
Yeah, it's possible. So in fact, this is done in an iterated fashion. You get rid of whatever you can eliminate and pretend they were never there because the truth is no one would ever choose them. And then what you have left, you just do it again. So it is possible, although not in any of the examples that we did.
Okay.
The second one is, and both of these I think are kind of obvious. They sort of make sense anyway, at least to me, that any Nash equilibrium will survive the iterated elimination of strictly dominated strategies. In other words, if you get rid of things that are strictly dominated, you will not accidentally get rid of Nash equilibria in the process. And that makes sense because if they're strictly dominated, then if you ever end up there, you would want to leave.
And therefore can't be a Nash.
And therefore can't be a Nash equilibrium. That's right. So those two things sort of make sense, I think. The last one is true, but isn't at least painfully obvious, at least not to me, and that is if n is finite, that is you have a finite number of players, and for each of the set of strategies, that set of strategies is also finite. In other words, you're still in a finite game. Then there exists at least one Nash equilibrium, which might involve mixed strategies.
So you're saying there's always a Nash equilibrium.
Yes, possibly mixed for any finite game. So when you said I relaxed everything, I didn't actually relax the requirement that it be a finite game.
Fair enough. But you stopped writing finite, so it's sort of the same thing.
Yeah, I agree. Because why would you play an infinite game?
I don't know. Maybe you got a lot of time on your hands.
That would be like an infinite jest. Okay, so those are the main results here. So what have we learned? What we've learned is that with interesting games, we end up in these weird situations where we have to figure out how to solve the game. And one really nice concept is this notion of an equilibrium, and in particular, the notion of a Nash equilibrium.
Cool.
And there you go. Let me just wrap up by doing a couple of quick things. Earlier on when we were talking, you made a kind of offhand comment about, or maybe I made an offhand comment about the fact that because we're doing this little prisoner's dilemma thing, and we have this sort of wall here, we're going to end up in this little bad place, right? With the -6, -6. And there was this kind of notion that what if we could hear each other? Would that make a difference? And the answer was no, not really, because whoever goes first is going to lose. And if you try to get people to go at the same time, well, in some sense, that's the same thing as having a wall and you can't hear each other if you have to go at exactly the same time, right? Does that make sense?
I didn't quite understand. Why does the person who goes first lose?
Because if I find out whether you're going to cooperate or defect, then I will just then do the thing that makes sense. So if you do anything but defect, I will defect, and then I will win, and you will lose. So whoever goes first runs the risk of the other person screwing them over. So
I see. Unless that person defects.
Right, but if that person defects, the other person is going to defect.
Right. So, but you don't lose any more than you would have.
That's true. But you still end up in this kind of unfortunate place. So one question you might have there is, well, yeah, but that's just because you can only do this once. But what if you could do this twice? So let's imagine we're going to be in this situation today, and then we're going to be in this situation tomorrow because, you keep leading me astray. So whatever happens today, I can use as information for what I might do tomorrow. So if I decide to go ahead and cooperate this time and you defect, then I know you're the kind of person who defects. And so when we're in this situation again, I'm definitely going to defect. So maybe in that situation, it's in your best interest to go ahead and cooperate because then we can keep cooperating together and in the end, it sort of works out. So maybe this notion of not just playing Prisoner's Dilemma once, but playing Prisoner's Dilemmas twice or 3 times or 4 times or 5 times might come to a different result.
Yeah, that seems plausible. I mean, I could imagine saying to you through this channel in the wall something that says, cooperate with me, or or I will stop cooperating with you, and so you get more reward if you cooperate with me.
Right. So my question to you is, what does happen exactly in this set where I have 2 versions, 2 consecutive games of Prisoner's Dilemma to play? What am I going to do?
Okay. Well, now, I mean, we can turn this into a game, right? I mean, that's what you were teaching us how to do.
Yeah.
So now the game has 4. Well, I don't know. I mean, so one way to do it is to say A has a choice to make on the first step, and and that could be cooperate or defect, and then the second step could be cooperate or defect. So there's 4 possibilities.
Right.
B has the same 4 possibilities. But maybe we can actually have A be responsive to B. So A has 2 things to do on the first step, and then 2 things to do on the second step for each thing that B did on the first step, for a total of 8 combinations. So
Right,
if we
you could
made
do
an
that.
8x8 matrix, we should be able to solve it.
Right. So that's pretty easy to do. You just kind of draw an 8x8 matrix in, that many dimensions, and you end up right here.
I wasn't thinking about that many dimensions. I just thought like the normal kind of matrix, but okay.
Oh, I see.
I mean, it's
Well-
8x8, so that's kind of a pain, right? So it's 64 cells, and I guess we don't want to fill that out.
Yeah, but you know what? We could fill that out, but I'm going to help you out here by pointing out, you know what? It's not going to make a difference.
Oh.
So here, let's see if I can walk you through why it's not going to make a difference. Let's imagine I have 20 of these games. Okay?
Sure.
So I'm going to play these games 20 times in a row. Now, what you've been doing is you've been going forward. You've said, well, if I can get us to do the right thing, or if I can basically threaten you and say, if you screw me over this time, I'll screw you over from now on, then maybe I can get you to do the right thing, and vice versa, since it's a symmetric game. And then we'll end up doing the right thing all along. And that makes a lot of sense, right?
Yeah.
If you're going forward. But what if you're going backward, Michael? Let's imagine we're doing 20. What's amazing to me is that is exactly backward what you just said. So let's imagine we're doing these 20, ... And now I'm on the 20th game, okay? What's going to happen on the 20th game?
Well, I mean, I guess I could have built up trust in you from the previous games and think that you're going to cooperate with me because we've been cooperating together. And then that would be the perfect time to drop a dime on you.
Exactly. So if this is the 20th game and we're in this situation, remember, whatever value we've been adding up along the way, that's sunk cost, right? The only thing that's left is the final game. And the final game looks like this, which means we're going to end up here. But guess what, Michael? The final one is determined. So since we already know the outcome of the final game, the next one that we can look at is the 19th game. Well, we already know what the outcome of the final game is. So this is effectively the last game.
Oh.
And what's the outcome of that going to be? It's going to be this. And backwards, proof by induction, because the only proofs computer scientists know how to do are proof by induction. It turns out that we will always defect.
For what it's worth, those are the only proofs worth doing, but okay.
That's
sure.
true. It's a fine point. Truth by induction and perhaps by conduction. So there you go, Michael. Even if I can play multiple games and try to build up trust, the truth is the Nash equilibrium, if I filled out that 8x8 matrix you wanted me to fill out, I would still end up in the same place where I would defect both times.
Certainly if you're going to be a jerk, then I have to be a jerk. But yeah, I guess that's right. That seems pretty horrible.
It is. And by the way, this is not just something I'm making up. This is another theorem that comes out of Nash equilibrium. That if you have an n-repeated game, then the solution is n-repeated Nash equilibrium. So whatever the Nash equilibrium is for the first game, the one version of the game is the repeated Nash equilibrium for all versions of that game.
Okay, wait, hang on. So I buy that.
Mm-hmm.
But couldn't you? Well, so in a game that has more than one Nash equilibrium, couldn't we alternate?
We could, and in fact, you'll notice that so far I have not talked about the case where you have multiple Nash equilibria, because in fact that's its own problem. If I have one Nash equilibrium, then we know what's going to happen. If I have two Nash equilibria, which one do we choose? Now, what's important to note here is that if we have two Nash equilibria, then that means that if you're in any one of them, you won't leave it. So it's not like you'll move from one Nash equilibrium to another, sort of in the general case, because the fact that it's in equilibrium means that if everyone else is fixed except one person, that person won't choose to move. But I haven't said anything about how you would choose among multiple Nash equilibria. And that's beyond the scope of this class.
Okay.
But it is an active research area. And in fact, some of my own students have done some work in thinking about what it would mean to choose. And actually, the answer always boils down to, let's not worry about that.
All right. But I'm still kind of disturbed by this, right? So 'cause it seems like it's sort of saying is if we knew the world was going to end tomorrow, then we might as well be greedy bastards. And in fact, if we know that the world is going to end at any particular time, which of course it will, we might as well be greedy bastards.
That's right. So be greedy bastards. Or at least be, Nash bastards.
Well, then Nash is kind of greedy, right? It's like I'm always taking an action that's best for me.
Yes, you are.
No.
Every single thing we've talked about today has always assumed that you're always doing what's best for you. The fact that it might also be best for someone else is neither here nor there. You're always doing what's best for you.
Right. I get that. But it sounds like this argument is saying that we might as well be like that like all the time and never really form like never self-sacrifice even a little bit for greater advantage even to yourself.
Well, that's not true. It's all hidden in the utilities. Once you've gone through all the what I'm going to do today, what I'm going to do tomorrow, and you add it all up, whatever the right strategy is to take, That's the strategy that you take because it's already accounted for all the self-sacrifice you might do that then leads to later good deeds or later good outcome. So the wonderful thing about all of this is that this matrix is everything you need to know. It captures the future, past, and everything else. It's everything you need to know is right here, and it's all been reduced to a bunch of pairs of numbers. But you did say something kind of interesting, though, Michael, which I think is worth pointing out, which is that everything you say requires knowing when, at least in this sort of iterated version, requires knowing when the world is going to end. So an interesting question to ask would be, what would happen if I knew the world was going to end, but I didn't know when? Would that change my behavior?
It doesn't seem like that should make any difference because it's still going to end. If not today, then tomorrow, or if not tomorrow, then the next day.
True, but I bet you it does make a difference.
I'm willing to go and think about that.
Okay, why don't you go think about it and let me know.
All right, I'll tell you about it in the next lecture then.
Okay, I like that. Excellent. Okay, cool. So let's move on.
Okay, fair enough.
All right, Michael. So I think that brings us to the end of what I wanted to talk about anyway. So can you help me remember what it is that we've learned today? In particular, what you've learned today.
Sure. So I guess the first thing I learned is that game theory can make you depressed. And in fact, in particular, that my friend Charles, given the opportunity, would totally drop a dime on me just to save a month of incarceration.
Yeah.
Wait, no. I don't think you summarized that correctly. Game theory is not depressed. It's depressing.
Oh, yeah, that's a good point.
And Michael is not cruel. He is the victim of cruelty.
I don't think so. Because you want to know what the secret here, Michael, is? You've got a little matrix of numbers. Those numbers capture what's going on. The truth, Michael, is that if we were in Prisoner's Dilemma, I would cooperate with you because my utility is not simply the number of months that I would spend in jail, but it's the number of months you also would spend in jail.
Ooh, interesting.
So if the best way to beat Prisoner's Dilemma is to change the numbers.
I see. It's like the Kobayashi Maru of game theory.
Exactly. So there's an interesting question for you right there, Michael. If I had Prisoner's Dilemma here, let's write it out so you can remember. If I had Prisoner's Dilemma here, we already know that we're going to end up here because that's what the numbers tell us to do. But what we'd have to do is change the game. So how would you change the game in Prisoner's Dilemma?
I see. So if we're thinking about it in particular in terms of I care about how long you spend in jail, maybe not as much as I care about how much I spend in jail, like maybe half as much, then the payments shift, right?
Right.
So now we have like -1.5 in the upper left-hand corner, -9, comma, -4.5, -4.5, -9, and -9, -9.
So
So now that bottom right becomes a lot less attractive if we actually care about the other person.
right.
Oh, that's okay. I'm less depressed now.
Except, of course, that requires that you feel that way internally and that I feel that way internally. There's another way that you could change the game here, which is what happens to snitches in jail?
They are rewarded.
No, they're not.
They're punished.
Yes.
Oh,
So if you're a part of the criminal fraternity and you don't like Prisoner's Dilemma, then what you have to do is you have to create a system where the people who snitch get punished. So it's not just the months that they spend in jail, it's everything else that's going to happen to them if they drop a dime.
so you're saying that -6 ends up being worse?
No,
No, the wait, what? Yeah. Oh, the 0 ends up getting. Oh, I see. The 0 ends up being worse because even though you're not in jail, you're going to get, I don't know, somehow thwarted or punished for your past behaviors.
accosted. That's
Interesting.
right. So that's what you have to do. And that works not just with criminals, but with the real world. Whenever you're in this sort of situation like a Prisoner's Dilemma, you can change the game by changing everyone's utilities. By, for example, hiring police officers or hiring members of the mob to take care of everything.
I see. So it almost seems like what you're talking about is a kind of inverse game theory, where if there's a particular behavior that I want to see, how do I set up the payments and rewards so that behavior is encouraged?
Right. And by the way, that has a name, and it's called mechanism design.
Mechanism design?
Yes.
I'm not sure I understand either of those words.
Well, that's where you're trying to set up the set of incentives, the mechanisms that you're using to pay people. You're trying to design them in such a way to get particular behavior. This is what a lot of economics is all about. This is what a lot of government is about. Tax breaks, for example, for mortgage interest, encourages you to buy a home rather than rent a home.
I see, by changing the payoff structure.
Right.
Oh, that's neat.
Yeah, and so that's what we learned today, at least right now.
Okay. All right. So let's see. So just to try to rattle off some of the other things, the whole notion of game theory we talked about, especially the idea that you can think about a game as a tree, or you could represent it as a matrix. And I believe you said repeatedly, the matrix has everything. Is that how you said it? Or the matrix is all you need.
Yep.
Let's see. We talked about minimax and maxi-min.
Mm-hmm.
We relaxed a bunch of constraints on games. So we looked at both perfect and hidden information.
Mm-hmm.
We looked at both zero sum and non-zero sum.
And we learned a lot today.
We looked at deterministic and stochastic, I would want to say, but you called it non-deterministic. And assuming that we can get rid of the first two bullet items that look like maybe they were jokes, I would suggest saying things like we talked about what strategies are and that they come in different flavors. We talked about the evil prisoner's dilemma game.
Mm-hmm. What else? You got to give me more, otherwise it's staying.
Oh, Moore. Good point. Andrew Moore gave lots of really good examples.
Yes.
Make this
Michael
lecture
may
help.
be cruel, but Andrew Moore is awesome.
He's more cool than me.
Andrew Moore is very cool. All of the examples that we've used today, or almost all of the examples we used today, actually come from Andrew Moore's slides. Andrew Moore is a professor at Carnegie Mellon, or at least he was before he went off to Google, and is a really smart guy who cares very much about machine learning and game theory, and produced a bunch of slides that it turns out lots and lots of people use in their own courses. And his examples were so good for game theory that I decided to co-opt them. With his permission, of course. He tells everyone that they may use them. And in fact, we have pointers to his slides in the resources links and folders for all of you to look at. And I recommend that you do. Did we learn anything else, Michael?
The only other thing that I would want to mention is Nash, which is a concept that is Nash-tastic.
It is Nash-tastic. There are, by the way, I should mention briefly, other kinds of equilibria concepts. They're beyond the scope of this class, but there's a whole lot more to game theory, as you might imagine. And sometimes when Nash gets you in these situations where you can't do what you want to do, you end up in these prisoner's dilemma situations, other kinds of equilibria can get you out of it. And I'm going to argue, without explaining why, that the way they get around it is by introducing other ways of doing various kinds of communication. And in fact, I claim they're a particular part of mechanism design. But that's a topic for another day.
Okay, fair enough.
Okay, did we learn anything else, Michael?
I don't know. That's what I was thinking about. I mean, that seems like a lot to absorb. And the other thing is that repeated games, even the prisoner's dilemma, kind of unravel if you know when they end. And I was going to try to look into what happens if you don't know when they're going to end.
Okay, so I guess that will be something that we will learn next time.
Right. What will we have learned?
Yes. Future past tense. All right, Michael, well, I think that's about it. At least my brain is full. So I will talk to you next time. And you get to lead what I believe is the last full lesson of the course.
Oh, exciting.
It is exciting. All right, well, bye, Michael. You have fun. I'll see you next time.
All right. Bye, Charles.
Bye.